Hi, multivariable calculus. Ms. Deer back on the mic today. I just wanted to finish section 15.2 with you in your textbook. We introduced live the idea of a line integral, and we talked last week about vector fields. So today we're going to talk about line integrals and vector fields. So what this is mostly used for is to find what we call work. And we find work, we find the work done on an object moving along a path. So in a field, if you have an object in a field, the work done by the force only matters when that force is either in the same direction that the object is moving or in the opposite direction that the object is moving. So the best way to think of this is if you have a river flowing this way and you want to swim with the current, the force is moving in the same direction as you. If you swim against the current, the force is working against you. And if you all probably heard that if you want to get out of a rip current, you swim perpendicular to the vector field, right? And then it is not doing any work on you. So when we consider this is, if you think about how much of the field is working on the direction an object is moving, we're looking at how much of F is on T. So this is the projection of the field onto T, where T is the tangent vector in the direction that the object is moving. So again, if you're swimming this way, that's the direction of your tangent vector. If F is going in the same direction, then there's a lot of work being done, right? If you're going this way and F is going this way, there's no work being done on your particular path. So if we're looking at the component, how much of F is in the direction that the object is moving, we want to look at the projection of F onto T. So this is the definition of work. So work is the amount of work that F does on this object, but along a curve. So we need to combine this idea of this vector field along a path. So work is the accumulation along the curve of the projection of F onto T. All right, well, so now we have F dot T ds. Remember that to find our T, this is our unit tangent vector. So this is going to turn into F dot R prime of T over magnitude of R prime of T. ds is going to turn into magnitude of R prime of T dt. Notice these are going to cancel out. So we get F dot R prime of T dt. So although this is the definition of work as we've defined it, the actual equation to find work is the accumulation of F dot, we call this dr. So this is a shorthand for R prime of T dt. So now we have the precise definition of work and a usable definition of work. So let's do an example. Let's find the work done by, let's say, F, let's just do two variables, F of xy equals xy I hat plus yj hat over C. Let's let C be, let's do a polar function, 4 cosine t I hat plus 4 sine t j hat. T is between 0 and pi halves. So this should look a little bit like the example that we did this morning, so it feel familiar to you. All right, so in order to find the work done by F over this curve, well, we're going to have to First, find r prime of t. When in doubt, take a derivative. So r prime of t is going to be negative 4 sine t I hat plus 4 cosine t j hat. So now we have f of x and y. We can now write f as a function of t. So f of x of t, y of t is going to be, well, instead of x, y, I have, here's my x and here's my y. So I have 4 cosine t times 4 sine t I hat plus y is 4 sine t j hat. So now I have f as a function of t. I have r and r prime of t. So now I can find my work. So work is the accumulation over the curve of f dot dr. All right, so this is going to be, remember we're going to turn this into the integral from a to b of f of x of t, y of t times, or dot, r prime of t dt. So to make this an actual integral we can use, this will be the integral from, what were my t-bounds? 0 to pi halves. So now I'm literally going to dot f and r prime of t. So this is going to be 16 cosine t sine t 4 sine t dot r prime, which is negative 4 sine t 4 cosine t all dt. So when I dot these together, I get negative 64 sine squared t cosine t plus 16 sine t dt. So now I'm ready to take the antiderivative, and it's just a normal integral. I see something and its derivative. Well, it would have been helpful if I had put that in. Now I see something and its derivative. So I'm good to derive. So I get negative 64 sine cubed t over 3 plus 16 sine squared t over 2. I'm going to evaluate that from 0 to pi over 2. So this becomes negative 64 over 3 plus 16 over 2 minus 0, which is negative 40 over 3, I really believe. All right, so there's a lovely, oh, I ran out of space for you. So there's a lovely example of in space in your book in this section that I would really recommend you take a look at. And I really want to emphasize, so I'm just going to write it down because I feel like anything I want you to remember I should write down, that the work done in the direction of the work done is in the direction of an object. So the total work done is going to be 0 if, well, r prime of t is orthogonal to f. So if you're moving perpendicular, you're not going to accumulate any work at all. All right, so one more topic that I want to go through here at the end of section 15.2 is another form that we often look at for line integrals. So if we have a vector field, so f of x, y is mi hat plus nj hat, and I have my curve C defined by a vector valued function, so r of t is x of t I hat plus y of t j hat. So again, here I have, oops, sorry about that, I have my vector field and I have my parameterization of my curve. So I can write f dot dr. Well, I can write this as the accumulation of f dot r prime of t dt, Well, look at what F is. F is M I hat and N J hat. So I'm really dotting here is M I hat plus N J hat dot R prime of t, which is X prime of t I hat plus Y prime of t J hat, all dt. So when I dot them, I actually get M times dx dt plus N times dy dt, all dt. And these sort of in our mind, right, will cancel. And so the shorthand version of this is to write M dx plus N dy. And this is called the differential form of a line integral. Also, obviously, we can also have m dx plus n dy plus p dz if we were in space. But this differential form is one you see a lot of times when we're being particularly lazy, and I definitely support exact laziness. So let me give you one example of what this looks like before I have you try to figure this out from reading your book. So if I want to evaluate the line integral, and let's do 3y minus x dx plus y dy, and I have to have a curve. So let's say C is given by x equals 3t, y equals 6t plus 1. Let's use t just between 0 and 1. Sorry, my scrap paper is apparently a little bit see-through. All right, well, I have a line integral to evaluate. It's in differential form. So I'm actually just going to find these things and plug them in. So I can see that instead of my y, I'm going to write 6t plus 1. Instead of x, I'm going to write 3t. Instead of dx, I'm going to write, well, let's figure out what I'm going to write. So what does dx equal? 3 dt. Instead of dy, I'm going to write dy equals 6 dt. This is a really easy way. When you're given this differential form, you can just turn this into, so my t values go from 0 to 1. So I have 3y, y is 6t plus 1, minus x, x is 3t, all times dx, which is 3 dt, plus y times dy, which is 6 dt. So this dt goes to everything. Because it's in everything, I can kick it outside. So let's do a little algebra, which we all know is my kryptonite here. So I get 3 times, I can't, 18t plus 3 minus 3t, all times 3, plus 6 times 6t plus 1 is 36t plus 6, all dt. So 18 minus 3 is 15, times 3 is 45t plus 9, plus 36 plus 6 dt. Oh, I think I'm there. 45 plus 36 is 81t plus 9 plus 6 is 15 dt. Easiest integral ever. So I get 81t squared over 2 plus 15t, and I evaluate that from 0 to 1. And I get 81 over 2 plus 15, so 81 over 2 plus 30 over 2 is 111 over 2. So the differential form is pretty easy to work with. It's just another way we can write that, and we can go ahead and solve it out. So please read section 15.2 in your book. Look at there's a great example of work in space, and you can get started on your homework.